or in hindsight of his question, can you say which color class it occurs in? So in particular, does there exist a large arithmetic progression in the largest color class, the color that's used most often, in a sense? So is it true? I think it's a conjecture rather than a question, so I'll just write it as a conjecture. So for every k and delta, there exists an n such that if A is a subset of 1 up to n, and size at least delta n, this implies there exists a k-term arithmetic progression in A. So every set of integers of positive density contains arbitrarily long arithmetic progressions. It is a slightly imprecise way of saying this. Does it make sense? This is a conjecture. So 1950, I think it was 1950, Roth proved the case k equals 3. Roth's proof used Fourier analysis. The proof is not extremely complicated, but it's very clever, and had consequences later on. I won't really have much time to talk about, or well, might talk about briefly. But even this is it's a non-trivial result. The next big breakthrough was in 1969 by Szemeredi, who proved the case k equals 4. It doesn't really seem like much progress is being made, but actually this was kind of the key thing. So in 1973, I think, Szemeredi proved it for all k. Okay. So 4 was the difficult case. Once you can do 4, then a similar but more complicated argument gives for all k. Okay. And the key tool that Szemeredi introduced in the proof of this is called Szemeredi's theorem, was this lemma about graphs. So this problem doesn't particularly look like it has anything to do with graphs, but as we'll see, it's actually intimately related. Okay. As I say afterwards, so 19... Am I getting this right with the 73? Maybe I'm getting this wrong. Maybe it should be 76 or something. Anyway, so 1977 or something, Furstenberg, I'm not sure how to spell, sorry, gave a second proof using ergodic theory. Let's see if I can spell ergodic theory. Like that. With a... Where? Ah, sorry. There. Okay. Like that? Is that right? With D. Okay. So this was actually this proof had a big impact on ergodic theory, and now there's a big branch of ergodic theory that's sort of was started by this proof. In 1998 or something, so 2 papers. Gowers then gave another proof of this result using Fourier analysis. So Gowers' proof was a generalization of Roth's proof. So I think this paper was the case k equals 4, and this was general k. This has also had an enormous impact on the topic of discrete Fourier analysis. This has led on to a large body of work.
That conjecture asks A to be monochromatic?
Oh, sorry. Now it's a subset. Yes, there's no coloring anymore. So in Van der Waals theorem, you have a coloring. Here you just have a subset. So you think of it as being one of the color classes. So it's saying if the color class, so here just if you color with R colors, then one of the color classes has size at least n over R. So this is saying that so here it says one of the classes has a monochromatic AP. Here it says actually this one does, the biggest one. Yes, it's a stronger result. And it's perhaps not obvious that it should be much harder, but it really is much harder. This is often the case that proving something, the Ramsey version of a problem, is easier than proving the extremal version. I mean, often the answer is just totally different, right? Like with, with finding a monochromatic triangle, so the extremal version says you need half the edges to force a triangle. The Ramsey version just says you need a sufficient number of vertices. So once you've got a sufficient number of vertices, you're just done. So it's not true that, so the corresponding thing with triangles would not be true. It is true that take n sufficiently large, color the edges with R colors, you find a monochromatic triangle. It's not true that if you take delta proportion of the edges, you have a triangle. Right? Just take a subgraph with a bipartite. Yeah. But in this case, it is true. Okay. And there are by now actually many proofs of this result using things like ultrafilters, using so various different techniques. According to Tao, there are about 20 different proofs or something, which I think he says somewhere are really, really different. But anyway, so I was about to say I knew one of them. I think I know none of them really well. So. So what we'll see, what we'll prove in this course, is we'll see a proof of Roth's theorem, but using Szemeredi's technique. Okay. So which is simple enough that we can really do the details, and it's not too scary. Okay. So today I just want to talk about this fundamental tool, this lemma about graphs that Szemeredi introduced, which turned out to have many, many, many other applications. Yeah. First, all these people are super famous. In case you don't know them, Roth won the Fields Medal around this time. Szemeredi won the Abel Prize recently, mostly for this. Gowers won the Fields Medal. Furstenberg has won lots of prizes, but I don't know exactly which. The Wolf Prize and probably the Abel Prize. I don't know. Yeah. So they're all like super, super famous people. Right. Okay, so what's the idea of the regularity lemma? So the rough version of the statement is, well, perhaps I'll say something first. So we've already seen that if you want to find something like a triangle, if you just know something about the number of edges, it's difficult. You need lots and lots of edges. You need more than half the edges. If you're looking for a triangle in a random graph, you need way fewer edges. Right? As we saw the other day, you need basically constant times n. Right? So the number of edges that imply there exists a triangle is n squared over 4. Number of edges in a random graph that imply there exists a triangle with high probability is roughly n. Right? So if you want to look for things like triangles, you're much better off if your graph is random than if it's arbitrary. Okay, sort of not so surprising. The idea is one of the ideas is that there's something that lives in between these two. So the number of edges in a sort of almost or random-like graph should be something like some small constant times n squared. Okay. So this is sort of the first idea that should guide us. That there exists this concept of being random-like, even though you're just a deterministic graph, which can help us do things like find triangles. So we're going to see exactly what this notion is. Okay. And then the statement is going to be, take any graph. Okay, you can't hope that any graph looks random-like, but somewhat shockingly, take any graph and you can break it up into a bounded number of pieces such that each pair looks random-like. It's not quite true, but it's almost true. So for every graph, there exists a partition of the vertex set into a bounded number of parts, so that if you look between two of them, you are random-like. That's not quite true in the following sense. Almost all pairs are almost random. So almost all pairs are random-like. So first, so we need some parameter that's going to measure almost all. That's going to be called epsilon. So we say that 1 minus epsilon proportion of the pairs are epsilon random-like. And then this k, this number of parts, is going to depend on epsilon, but not on n, the number of vertices of the graph. Okay? So this is the basic idea, that we're going to take any graph we like, we're going to fix a parameter epsilon, which is going to be a small constant, and say, right, I want to break up into a bounded number of pieces where the bound depends on epsilon, and 1 minus epsilon proportion of the pairs are going to be epsilon random-like. Okay? So let me define what I mean by epsilon random-like. So pair AB, so subsets of vertices, is epsilon regular. This is going to be epsilon random-like if, okay, if what? Now let's think. What would be a good notion of being random-like? So what do I even mean by that? What does this question mean? I mean I want a deterministic condition about this graph. So what do we have? We have we have a set of vertices A and a set of vertices B. And we're interested in the edges between the two, from A to B. I would like a deterministic property of this graph which tells you that this graph is in some way random-like, or some way looks random-like, or shares various properties with a random graph. So what properties of a random graph would we like to force? What are some simple properties? So suppose that these edges were chosen randomly, with probability of half or something. Tell me some properties that you would typically have of this bipartite graph. Just some simple properties.
There would be p n squared.
Yes. So right. So suppose the density is, let's call it d. There would be about d, and let's suppose these are size. Maybe I'll call them n each. Okay. Maybe d times a times b edges. Okay. But this is, I guess, almost a tautology because this is the definition of D, right? So, okay, so that's how we define D, but that doesn't tell us anything yet. So yeah, so what more can we say? So
Maybe about the degree of the vertex.
it's a good idea. So in a random graph, all the vertices have roughly the same degree. Okay, if the density is positive. Let's think of the density as being a half or something. Okay, so the degree, the number of neighbors of U in B should be roughly should be roughly the same for all vertices in A, and vice versa. Yeah, so the degree should all be roughly the same. Is that going to be enough to, say, find a triangle? Okay, not going to find a triangle here because it's bipartite, but to look for particular subgraphs. So suppose you weren't bipartite anymore. Suppose you just knew all of the vertices had the same degree. Would that tell you a random-like in a useful way? In particular for, say, finding a triangle. Well, here's a counterexample. In this graph, all of the vertices have the same degree, but it doesn't look at all random-like, right? It's a complete bipartite graph. Okay, so just controlling the degrees is not enough to tell you that a graph is random-like. Sorry? Right, so we've already said that we're going to define D to be by the number of edges. Yeah, so we have a certain number of edges. Let's suppose it's half of them. So let's define D to be this density. So it's a half. But yeah, what extra conditions would we expect? What conditions does this thing fail that?
Some variance.
Yeah, so that's true. It's a more complicated. I mean, so it's true that you would expect, if there was random, the degrees to have a certain distribution. It's not really clear how to use that, right? I mean, you could just kind of mess around with this and force it to have the right distribution. I mean, whatever degree distribution you want, you can just kind of stick it in.
Maybe have that each subgraph has similar properties.
Yeah, now we're getting much closer. This is a great idea. Right. So let's look at, you said subgraph, but I guess what you mean is pick like subsets of the vertices. Right, so suppose you pick a subset of the left and a subset of the right, x and y. So what might you expect in a random graph to happen between x and y?
Satisfy the same thing.
Yeah, they should have the right density, right? The density between x and y should be close to D. And that's all we ask for. That's the property. Okay? So, if for every x in A and y in B, okay, it shouldn't be for all because small ones are going to mess you up. It's all large ones. So size of x is at least epsilon times A. Size of y is at least epsilon times B. So here's the first time the epsilon appears. Then the number of edges between x and y divided by x times y. So the density between x and y minus the number of edges between a and b over a times b. So the density between a and b should be close to each other, should be less than epsilon.
Why this doesn't happen to a bipartite, complete bipartite graph?
Sorry, so a complete bipartite graph does satisfy this with d equal 1, the density being 1. Yeah, sorry, so I was jumping out of the bipartite world. So if in the whole world you just knew the degrees, it wouldn't help you. You come up with an example in the bipartite world as well, but it's harder to see. So yeah, so you should, sorry, it was misleading. So complete bipartite graph does satisfy this property. So that pair is epsilon regular. Yeah, so what do I want to say? Yeah, you'll see. So this will be useful when you have many parts. So we don't just want sort of 2 parts, a small number, not really many. Okay, so this is not such a complicated definition, right? For every pair of large sets, you have the right number of edges between them. Okay. So why is this useful? So let's prove a lemma. So I'm going to just draw a picture of this lemma. And then we're going to prove it by picture as well. Uh-huh.
What happened with the condition that about the degrees?
So we'll see in a second. Yeah. Yeah, so it's coming back. But it's not included here, you're right. Yeah. Okay. So suppose we have 3 sets A, B, and C. And suppose AB, AC, and BC are epsilon regular. And let's suppose their density is also bounded from below. So let's say they're delta dense, meaning the density, so I'll just say it for AB, over AB is at least delta. And the same for AC and BC. Okay, so they're all epsilon regular and delta dense. I would like this to imply that there exists a triangle. Okay, so here we're epsilon regular and delta dense. Here we are, and here we are. Right, so we're going to, so there's going to be a condition on epsilon and delta that we'll see in the proof. Or perhaps you can start to think about now. Yeah, so this is going to be more likely to be true if delta is bigger, because we have more edges, and if epsilon is smaller, because then we have a stronger condition. Okay, so it's going to be, so I'd really like it for all delta. If epsilon is sufficiently small, then this is true. So for all delta exists in epsilon. Okay, so how are we going to prove this? How are we going to find a triangle in this picture? Yeah. Oh, sorry, they're big. Yeah. So I also want let's call it n and say it's large. Yeah. So I'll state this more formally later. But right. Okay. So delta is fixed. So you're given delta. There's an epsilon which depends on delta, and an n which is a function of both epsilon and delta. Okay, which is large, and they're all of size n. So n here, n here, and n here. Okay, so I think this is not obvious. So let's start with a simpler observation. So we need to find a way to use this definition, right? It's not clear how to use it. So here's one simple way of using it. So observation. So what we said, so now we're going to come back to degrees. What can we say about the degrees in an epsilon regular pair. Right. What we wanted was that they were all close to each other. So can we prove something like that? So what can we prove about the degrees in this pair given this definition? Implies what? So I don't claim that every degree has to be close to what it's supposed to be, because you can't say anything about every degree, right? There could be, if you add a vertex that isn't attached to anybody, or is attached to everybody, it doesn't really change this condition very much. You don't see it in this condition. Right? So you can't say anything about individual vertices or even small groups of vertices. What you can say is about big sets of vertices. So I claim not that every vertex has degree roughly correct, but almost all vertices have degree roughly correct. So I claim that at least 1 minus 2 epsilon times A vertices of A have degree in 1 plus or minus epsilon times D times B, where D is the density of the, this is the density. Does it make sense? So the density is D. So you expect a vertex on the left to have about D times B neighbors. Right? Or you might expect. On average, that's true. You're looking at me from crazy. If the density is D, then on average, the average degree of a vertex over here is D times B. Right? So this is the average degree. This is saying that degrees are all between 1 minus epsilon times the average and 1 plus epsilon times the average. Concentrated near the average. I'm saying not all of them, but almost all of them. 1 minus 2 epsilon times A of them. Does the statement make sense? Okay, so now prove it. The hint is the proof is easy. Okay? I mean, it's an observation. Really, the proof is like 2 lines. No, we only use this definition somehow. Right? Yeah, sorry. I mean, it follows easily from the definition. But you have to find some way to use this. So, what does the definition say? It says for all x and all y, this. So, what is x and what is y? So if you take x equal to A and y equal to B, then this is 0. So it tells you nothing. Yeah, so at least one of them has to be something clever. X should be a set, not a size, not a number. So I'm going to find a set x.
The set doesn't satisfy the property.
There we go. We're interested in vertices of A with certain degrees. So why don't we define x to be the vertices with, let's not do them both together, let's just do the vertices of high degree. Okay? So that x equal u in A such that the number of neighbors of u in B is more than 1 plus epsilon times D times B. Good. Okay, what's y?
Maybe neighborhood of x.
That would work, but then I have to add extra notation. So I'm taking it even simpler. I mean, x is big, right? We're worried about x being big, so probably the neighborhood is everything. Let's just take y to be everything. Okay, and how many edges are there between x and y? Yeah, at least 1 plus epsilon times d times b per vertex of x, so times x. But this says exactly, so if we divide by x and divide by b, which is y, let's divide by x and divide by y, and then subtract d. What am I talking about? Yeah, sorry. Sorry. Stupid, annoying mistake. But I shouldn't multiply my epsilon by d. So d plus or minus epsilon times b. I mean, it's almost the same thing, right? Because d is a constant.
So what's the problem with the...
It doesn't quite fit with what I said. I mean, it doesn't quite... I want a constant 1 here, not d. It's just the way I wrote it. I mean, it's basically equivalent. So, yeah. Sorry. So I'll just slightly change the statement. It's basically the same, right? As long as epsilon is much smaller than d, then it's basically the same. So I need to put this here as well. D plus or minus epsilon times b. And now, let me do it again. This is at least d plus epsilon times b times x. So what? Exy over x times y over x times y. Cancel, 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 cancel. Minus d is at least epsilon. Contradiction. So what do we conclude?
X has less than...
Exactly. This implies that the size of x is at most epsilon times a. Right? Because if it was at least epsilon times a, then the condition would tell you that this didn't happen. Okay, but x is most epsilon times a. Exactly the same argument for d minus epsilon tells you there are few vertices with low degree, and therefore you're done. Okay, so that was the observation. So it's really just exactly the definition applied to the correct choice of x and y. Okay.
Can you repeat that part?
Yeah, please.
For
So if I just do, sorry. This was for plus. If I just write minus less than or equal to,
then you take
and it's,
subsets.
so just take this.
Spontaneous, that one and the other.
No, I take exactly this one. So I apply, so the proof is in 2 steps. You apply the definition to x and y defined as greater than equal to and plus, and you find that x is at most epsilon times a. Then you do the same thing for this set, and you find that this x is also at most epsilon times a. Then you just take the union of the 2 sets. And that has size at most 2 epsilon times a, and those are the bad ones. Right? So the epsilon a with degree 2 high, and epsilon a with degree 2 low, at most. Okay? Yeah? Everyone happy? Okay. So that was practice with the definition. Now let's apply this observation to prove this lemma. So why is this observation basically enough to prove this lemma? So let's try and apply it. Right? So we have some epsilon regular pairs. So AB is an epsilon regular pair. Right? So that tells you by the lemma there exist at most, I guess by the proof of the lemma, at most epsilon times A vertices that have low degree to B. This is said at most 1 minus epsilon times delta times B edges to B. Right? Because the density is at least delta. So the number of vertices that send few edges to B is at most is small.
Isn't it delta minus epsilon times?
Thank you. You're quite right. Thank you very much. Yeah. Is it better now? Right. Okay, so the density is at least delta. So if you send fewer than delta minus epsilon times B edges, then you're definitely in the too low set. This is x over here. And so you must be small because you have the wrong density. Right? Is it okay? Yeah, please ask questions now, because this is supposed to be the gentle introduction to this, and if you're lost now, then you're going to be more lost later. Because I'm going to start using these facts without explaining them. Okay, so this is the time when I'm supposed to be explaining them, when you're supposed to be understanding them. So that later you'll be like, yes, yes, yes. Throw out the vertices, high degree, done, 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 done. Right? So, should I explain this? Let's define, let me just prove it again. Let's define a set X to be the set of vertices whose degree to B is less than delta minus epsilon times B. Right? That's the definition of X. If X, I claim that the size of X is at most epsilon times A. If not, consider X and Y being the whole of B. Number of edges between them is at most this times X, which is stiff, and the density is at least delta. So the difference between the density between X in this set and A in this set is larger than epsilon. Contradiction. Okay? Okay, good. Okay, so let's get rid of those. AC is also epsilon regular delta dense. We do the same thing. Let's get rid of a set which is the ones that at most delta minus epsilon times C to C. I claim there's a vertex left, and I choose it. That's true if epsilon is at most a half. Okay, we get to pick epsilon. We'll make sure it's less than a half. Now, what do you know about this vertex? You know it has lots of neighbors here and lots of neighbors here. This set is at least delta minus epsilon times B, and this set is at least delta minus epsilon times C. Right? Still with me? So why are we done? Huh? Oh, okay. Right. Thank you for telling me. This is important. So, first step was remove a set of vertices that have low degree here. Remove a set with low degree here. Pick a vertex that's not in either set. So it has high degree in both. That's all we've done. We have one more step and we're done. How do we finish? We're trying to find a triangle. So where's our triangle going to be? What do we need? We just need a single edge between here and here. Why is there a single edge between there and there? Exactly, because BC is epsilon regular. So I'm going to call this x and this y. As long as this set is at least epsilon times c, and this one's at least epsilon times b, then the density between them must be at least delta minus epsilon, and so there must be at least one edge. Right? So you just need epsilon to be less than 2 delta. Right? Nothing terrible. Did it make sense? And maybe n is at least, what should n be at least?
You just need to pick a vertex in there, right?
So you need to pick a vertex in here, but that's epsilon less than a half. You need there to be at least one edge here. So you want, if the density is delta, so you want delta cubed times n squared to be bigger than 1 or something. So the expected number of edges is large.
You mean epsilon less than half of delta?
Thank you. Thank you. Thank you. And n should be like something like 2 over delta cubed or something. Nothing terrible. Or delta minus epsilon cubed or something. Anyway, whatever. Okay.
Why you need cube?
Because these guys have size delta n and delta n. So the expected number of edges between them is delta times delta n times delta n. Oh, sorry, to 3 over 2. Yeah, sorry. Sorry, because n squared. This is delta n times delta is delta cubed n squared, and that should be bigger than 1 or something. Bigger than 2. But, well, I mean, whatever, it doesn't matter. I don't want to confuse you. N is large, right? Delta is fixed, epsilon is fixed, n is huge, right? Okay. Right. So, you see from this that this condition can be used. You can use it to find subgraphs, so you can use to find triangles even when the density is only delta. Right? You have arbitrarily low density, you can still find a triangle as long as you have this quasi-randomness property. And this generalizes, we'll see next week, so you can prove a much more general embedding lemma of this type. So if you have more sets with epsilon regular delta dense between them, you can find larger subgraphs by essentially the same argument. Okay, so now we've motivated it. Let me try to state the regularity lemma. Okay. So for every epsilon and every k0, so we'll see the point of this in a minute, or in the applications perhaps, there exists a k1 such that for every graph, no matter how big, right? Epsilon is fixed, k0 is fixed, k1 is a constant, g is now huge. It's way, 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 way bigger than any of these numbers. Okay? all G, there exists a Szemeredi partition What is that? It's a partition of the vertex set of G into k parts with the following properties. K is between k0 and k1. First property. Okay? So the main thing is that k is bounded. It's at most k1. It just depends on epsilon. But in applications, we'll want it to be bounded below as well by some other constant. Okay. The size of the sets is all basically the same. So Vi and Vj are all basically the same. So they might not be exactly the same because of divisibility. Right? Maybe you can't, maybe your n is a prime or something. Right? Number of vertices. But they're as close as they can be. And most importantly, the pairs Vi, Vj, other than almost epsilon k squared of them, are epsilon regular. Is that understandable? I don't know how to say all but at most epsilon k squared of the pairs. Is there a better way to say it? Portuguese speakers. It's okay? Okay. Okay, so there are most epsilon k squared pairs ij such that Vi, Vj is not epsilon regular. Okay, does the statement make sense? Some sense. Okay. Okay. Okay, so I only have 15 minutes left. So let me sketch very quickly how to prove the Erdös-Stone theorem using the regularity lemma.
The second bullet, it means that the difference between the sizes are at most 1.
Yeah. So I can.
Sorry, you said that graph G was very big, right?
Yes.
But any condition on how big?
Right. So when it's small, then the condition becomes trivial because you just partition into individual vertices. Yes, it's only really a strong statement when G is large. Yeah. Yeah. So you think of G as being very large. Right. So perhaps first I'll just state this more general embedding lemma because we're going to need it, or at least I'll state one version of it. So. Something I forgot to say, so next time. So we should call this the lemma G Magulio or something. I don't know. Anyway, whatever. Embedding lemma. So for every H, so H is a graph, every delta, there exists epsilon and n such that if A1 up to AR have size n, where R is the chromatic number of H, maybe I'll say at least n. They don't even really have to be the same size, but yeah, perhaps I'll just say it in this slightly more general form. If they all have size at least n, and AI AJ is epsilon regular and delta dense for all ij, with I not equal to j, then H is contained in the graph. So what's the picture? Just what we had, but H is now something slightly more complicated. Here's H. A1, 2, A3. And you can find this H in this triple, if they're all. Okay, so the proof of this is a little more complicated than the one we saw, but not really, not much more complicated. Okay, is the statement clear? Okay, so we'll prove this next week. It's not difficult. Okay, so let me do this very quickly and not too precisely, and don't worry if it doesn't make sense. Next week we'll do it slowly and carefully. And then we'll do 5 more examples, applications that are similar, and you'll get the idea of what's going on. Okay? What do we need? What do we claim? The extremal number of H is 1 minus 1 over chromatic number minus 1 plus little o1 times n choose 2. So, proof. So the lower bound is easy. It's just the Turan graph. We're proving the upper bound. So let's assume that G is a graph with at least 1 minus 1 over R minus 1 plus, let's call it alpha. I think I'm going to just go ahead and call it delta. N choose 2 edges, where R is the chromatic number of H. Okay? So we're given this graph. It's got lots of edges. We want to find H inside it. Okay? We have a tool over here which lets us find copies of H. So let's try to get ourselves in that situation. Right? What do we do? So we apply the regularity lemma to give us a partition into k parts. I should apply it with epsilon and k0. So what do I mean? I'm going to mean epsilon is small, chosen later, and k0 in all of our applications, k0 will be 1 over epsilon. Okay, so just do it without thinking. You'll see why in a second. Okay. Now, we're going to define a useful object called the reduced graph. What is the reduced graph? So we'll call it R. Its vertices are going to be 1 up to k, so corresponding to the classes. And ij is going to be, so the edge set of R is going to be the set of ij such that vi vj is epsilon regular and delta dense. So I have to pick a delta to define this with. This delta, I think, will just end up being this delta. Right? So we have a delta given to us by the number of edges in the graph, which is arbitrarily small because we're trying to prove little o1. That delta will go here, and this epsilon should be chosen according to this lemma. Right? So delta is given to us. We choose epsilon small enough so that we can apply the embedding lemma. OK. And now what can we say? What can we say about the graph R? Using the embedding lemma. So the
It will contain 8.
So say it louder.
Using the embedding lemma, it will contain like a copy of
If what?
if we have that each component is large enough
Yeah, so what does that correspond to in R?
to have
What does the condition of the embedding lemma correspond to in the reduced graph? It's R classes, our vertices of the reduced graph, so every pair is epsilon regular and delta dense. It's a clique. Right? So if there's a copy of KR in R, this implies that there's a copy of H in G by the embedding lemma. Right? The embedding lemma says exactly that if there's a copy of KR in the graph, then there's a copy of H in G. So in that case, we'd be happy. So let's assume not. So what happens if there's no KR in R? Yeah, please.
How do you know that you can bound by the law with that n? The size of the
Good question.
yeah,
Good question. So we're given the graph with this property and n sufficiently large, right? So we're proving it asymptotic. So, and k is bounded above by a constant depending on epsilon only. Epsilon is only a function of delta and h. So k is bounded above by a function of delta and h. So as long as n is much bigger than that constant, this one here, then it's big. Yeah, so thank you. So it's a very good question. Did it make sense? OK. So once again, if it doesn't make sense, don't worry. We'll do it more slowly next week. It will start to make sense. OK, so what happens if KR is not in R? No, I don't need any of this stuff anymore. I'll go to this. What do we know about graphs that do not contain cliques of size R? Yeah, we have Turan, right? We know that the edges of R is at most 1 minus 1 over R times k choose 2. R minus 1. right? Maybe some tiny error term, but basically this. Okay. So now how many edges are there in G? On a bound from above, the number of edges in G. And I want to get a contradiction. Right? So, what kinds of edges are there in G? I claim there are 4 kinds of edges. So, here's the Szemeredi partition. There are edges that are in R. There are edges of G that correspond to edges of R. Then there are edges of G that correspond to things that are not in R. But why are they not in R? They're either not regular or not dense. There's 2 more parts. So here's a pair that's not regular. And here's a pair that's not dense. Okay, so there's 3 different kinds between parts. And then finally there's the ones inside. Okay, so let's bound each of them. First, the ones in R. How many edges of G correspond to edges of R at most? Yeah, so number of edges of R, which we've bounded, times each edge of R corresponds to how many edges of G. So how large are these sets? They're all of size n over k, right, basically. This is n over k squared. Okay, that already gives us basically what we have over here, except there's this extra delta that we need to use now. So what else do we have? Plus. So how many edges are inside parts? Well, each one might be a clique. So it might be n over k, choose 2. There's only k of them. This thing is at most n squared over k, which is at most n squared over k0, because k is at least k0. This is where we use it, the only place, which equals epsilon n squared. Right? There's only epsilon n squared edges inside the parts. How about between not regular parts? Well, a non-regular part could be pretty dense, so it could be as many as n over k squared. But how many do we have? By the regularity lemma, at most epsilon k squared, which equals epsilon n squared. So the epsilon n squared edges between these not regular ones, and what about the not dense ones? Well, maybe all of them are not dense, but how many edges does a not dense pair have? It's got density at most delta. So if you take all of them together, you still have density at most delta, which is delta times n choose 2, which is at most delta n squared over 2. This plus this plus this is less than delta, whatever. Okay. I guess over 2 plus 2 epsilon n squared. And this is a contradiction of our assumption. And that's it. Right? So this theorem that we really struggled to prove a few weeks ago, and which we only did it in the case currently being 3, follows almost immediately from the regularity lemma, plus this embedding lemma, which is not much harder than the thing we did. It's the same plus an induction. Okay, there's some slicing. Okay, we'll do it next time. You need some mini ideas, but it's really not complicated. Okay? Right. And there are lots and lots and lots of other applications like this. So we'll see a few of them next week. Yeah?